today we are starting Unit 4 on properties of a quadratic function. Now in Unit 3 we looked at solving quadratic equations. We're going to take what we learned in that unit and apply it to Unit 4 here, where we're actually going to look at the shape of those equations that we've been working with. At the beginning of Unit 3, I kind of gave you a little preview with a few examples, such as projectile motion and in business with revenue. And so we're going to take some of those and apply it now in Unit 4. So let's just get started. A quadratic function is any function that can be written in the form y equals ax squared plus bx plus c, which we should already recognize from Unit 3, where a, b, and c are members of the reals, and a cannot equal 0. Because if a equaled 0, then we wouldn't have a quadratic equation here. Now, this is called the general form of the equation of a quadratic function. So I'll introduce a different form of equation in our next lesson. So right now we're still working with general form. So right here I have a couple examples of what a quadratic function looks like. So you'll see that we have two different types here. One that is opening upwards and one that opens downwards. So the difference between those two here is that the leading coefficient on this is an x squared with a positive, and the leading coefficient here is a negative x squared. So we have a negative. So when things are positive, we are smiling, opening up, and when things are negative, we are frowning and opening down. A couple other things about the graphs here are the vertexes on both graphs. You'll notice that as a side note, they each say either a minimum point or a maximum point, and that is completely true. On our first graph here, we have a minimum point. This is our smallest point of our graph. And then on our sad graph over here, we have a maximum point, our highest point on our graph. And for both cases, those are called the vertex. The vertex will be the maximum or the minimum. Another piece that we see here are the axis of symmetry on both graphs. You'll notice it's this line, this vertical line that intersects the graph right at the vertex on both. And it splits the graph right in half. So it is split the graph into even halves because they are symmetrical here. So the axis of symmetry is an equation that's going to split our graph. So the graph of every quadratic function is a curve called a parabola. So both these graphs here are parabolas. All right, let's look at some characteristics of parabolas that we have already mentioned and a few others. So first of all, we have the vertex, which we said was the maximum or minimum point of a graph. And here it is a coordinate point. So when we're dealing with x, y coordinates, we're going to have a point as so, x, y. The axis of symmetry intersects the parabola at the vertex, just like we said, and the parabola is symmetrical, having two even halves about this line, which is a linear equation. So our axis of symmetry is just going to be an x value, which we got from our vertex, actually. It is just the x value of our vertex. That is our axis of symmetry. The y-intercept is the point at which the graph crosses the y-axis, and the x-intercept are the points at which the graph crosses the x-axis. Those are fairly straightforward. Now these last two here are very important when we're talking about properties of our parabolas. So the domain are all possible values of x for our graphs here. So if we go back up and look at our two parabolas, our x values are our horizontal distances, right? So as we increase or decrease our x values, our parabola is just going to constantly stretch out in the direction that it's already going. And hence is why we say the domain always is x as a member of the reals, because it's just going to keep increasing or decreasing in both directions for x values. Now the range, however, is a little different. Now range is all possible values of y, and it depends on the position of the vertex. So if we go back and look again at our parabolas here, we have our minimum point and our maximum point again. And those are either our smallest points or our highest points for our y values. So depending on which graph we're looking at, we're going to have a restriction on our y value. So for example, on this, our y values have to be greater or equal to the vertex point in this graph. And in this graph, they need to be less than or equal to the vertex y value for this graph. Let's try some examples now. All right, example 1. Graph y equals 2x squared plus 4x minus 6 for values -4 to 2 for x. Determine the intercepts, the coordinates of the vertex, the equation of the axis of symmetry, and the domain and range of the function. Alright, so to graph this, the first thing that we can use to help us is a table of values, just like we've used before in linear equations. So here we go. But what values should we use? Well, the question actually gives us that right away. We should use -4 to +2. So we have -4, -3, -2, -1, 0, 1, and 2. Now to find the y values that match these x values for our function here, we could go ahead and sub those into the equation and solve for y. However, there is another way that's much simpler. We can use our graphing calculator here to assist us. So let's go ahead and turn that on. If we go up to the y equals here, we can enter our function here, and we have 2x squared here, and then we have plus 4x minus 6 as our function. Now if we hit second function table over here, it gives us a table of values. Let's look at values from -4 to 2, just like that, and we're going to get 10, 0, -6, -8, -6, 0, and 10 for all the values of x that we have. Well, let's go ahead and plot that. I'm going to use a bright color like this pink here. So our first point we have at -4, 10, which is 1, 2, 3, 4 over and 10 up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, way up here at the top of my graph here. And then we have -3 and 0. So we got 1, 2, 3 right about there. -2 and -6. 1, 2, 3, 4, 5, 6 sits around there. -1 and -8, which is 1 and 2 down over here. And then we're going to have 0 and -6 about there. 1 and 0, which is about there. And 2 and 10, which should be about there. Now, if we went ahead and started up here and connected all our dots like so. There we go. We have a parabola there. Now, just a warning that I'm not an artist, so I know my parabolas won't be quite perfect. And if yours aren't either, that's okay. Just make your little points here a little bigger, making sure that they all connect. Alright, so there we go. So there's our parabola there. Now since we have graphed our function here, we can take what we see as the graph and our points to determine the intercepts, the coordinate of the vertex, the equation of the axis of symmetry, and the domain and range. So first of all, the intercepts. Let's look at those. Let's look at our x-intercepts first. So our x-intercepts are when the function crosses the x-axis, and we have two, one here and one here. And the coordinates of those x-intercepts here are 1 and 0, and then -3 and 0. So we have x-intercepts 1, 0, and -3 and 0. What about our y-intercepts? Do we have anywhere where the function crosses the y-axis? And we do. At this point down here it does, which is the point of -6 and 0 there. So we have y-intercept of -6 and 0. Perfect. Now the coordinate of the vertex here is going to be at this point here, our minimum point. And that coordinate then is -1 and -8. Our vertex here is -1, -8, our smallest point of our graph. Hence, from there, we know what the axis of symmetry is, and that is going to be the x value from our vertex, which is x equals -1. That's the axis of symmetry. Lastly, we need to decide what the domain is and what the range is. Well, since it's a quadratic function, we know that the domain is always going to be x is a member of the reals. But what is our range here? For what values of y is this function? Well, we look at our minimum point, right, from our vertex here. So in this case, we have that our y values need to be greater or equal to -8. However, looking at just this function and the fact that it gave us a restriction for x values, we need to alter these statements a little bit. Instead of just having member of the reals, we can say that our domain has to be greater or equal to 4 and less than or equal to 2 based on this question. And hence, with the graph ending at the top there of y values of 10, we can say that y values have to be greater or equal to -8, but less than or equal to 10. Just in this case, but both are correct. Now, if the x-intercepts cannot be identified from the table or graph, they can be determined by solving the related quadratic equation. That is, the intercepts are the values of x when y equals 0. Now this is where we're going to apply what we learned in Unit 3, so that way we can graph here in Unit 4. Now it says, example 2, determine the x-intercepts of the graph by solving the quadratic equation, -2x squared minus 6x plus 20. Now these are sometimes called the zeros of the function. So they are the x-intercepts, but also called the zeros of the function. So let's go ahead and use what we've learned in Unit 3. We have a quadratic equation, -2x minus 6x plus 20, and it's equal to 0 now because we set y equal to 0. From here, we can go ahead and solve by factoring. Let's take out a common factor of -2 right away. And we're left with x squared plus 3x minus 10 equals 0. Now this quadratic here, x squared plus 3x minus 10, is actually factorable. So we could go ahead and create the two binomials for that. And here we need two values that multiply to -10 and add to 3, which are x equals -2 and plus 5.